Hello, and welcome to another example of how to use logarithmic differentiation to find dy dx for a function that involves products, powers, quotients, and also if in another situation you have a variable base to a variable power. In this particular problem, we want to find the derivative of y equals the 7th root of x squared times the quantity 2x minus 7 to the 3rd power divided by the quantity 4x plus 5 to the 5th power. So this has a lot of powers, products, and a quotient, and it's perfectly suited to work using our logarithmic differentiation. Now notice when I have this function, I can rewrite my expression to the 1/7 power to write it without using the radicals, but instead using my fractional exponents. Then next up, we see that with all the products and powers, there's not a logarithm originally in this question. But I know that with the way this function is, with all those products, powers, and quotients, having a log would actually help immensely. So I'm going to incorporate the natural log, but since I'm doing it as a new process, I have to incorporate the natural log to both sides of the equation. Now what does that do for me? What it does, it allows me to use the properties of logarithms to expand out that right-hand side, and it helps me enormously not having to do as in depth with as many layers of the chain rule. So what we're going to do is we're going to use the properties of logarithms to expand that right-hand side. So we have the natural log of y is equal to, well, this is the natural log of a quantity to a power, so that 1/7 overall exponent can come down in front. Next, the natural log of a quotient is the natural log of the numerator minus the natural log of the denominator. And since I'm turning it into two terms, I need to put brackets around the expression. Next, the natural log of a product, and I have that in my first term, is the natural log of the first factor plus the natural log of the second factor. So natural log of x squared plus the natural log of 2x minus 7 to the 3rd power minus the natural log of 4x plus 5 to the 5th power, and then I can bring the exponents in the individual terms of the natural logs acting on quantities to powers as coefficients just in front of those terms. So the natural log of y is equal to 1/7 times, so this is 2 times the natural log of x plus 3 times the natural log of 2x minus 7, and then minus 5 times the natural log of 4x plus 5. Now again, these are all properties of logarithms that we're using. We haven't differentiated yet. Then one more step before we differentiate, we're going to distribute that 1/7 through. So I have the natural log of y is equal to 2/7 times the natural log of x plus 3/7 times the natural log of 2x minus 7 minus 5/7 times the natural log of 4x plus 5. Now that I have this out as term by term and I've brought all the exponents down, I've simplified it as much as I can with the properties of logarithms, we are going to go through and take the derivative. And because there's an action on the dependent variable y, we need to use our implicit differentiation on that left-hand side when we go through and do that. So remember, the natural log of something is 1 over the something times the derivative of the something. And the derivative of y is 1 dy dx. So that's where your implicit differentiation comes in. Now, on the right, we're going to differentiate this term by term. So I have 2/7 times the derivative of the natural log of x is 1 over x. And then plus 3/7 times the derivative of the natural log of 2x minus 7 is 1 over 2x minus 7 times the derivative of 2x minus 7. And the derivative of 2x minus 7 is 2. And then minus 5 over 7 times the derivative of the natural log of 4x plus 5, and that derivative is 1 over 4x plus 5, times the derivative of 4x plus 5, which is 4. So now simplifying this, we're going to move it up a little bit to get some more space. I have 1 over y dy dx is equal to 2 over 7x plus 3 over 7 times 1 over 2x minus 7 times 2 is 6 over 14x minus 49, and then minus, and I have a 5 over 7 times 1 over 4x plus 5 times 4 over 1, so that is a 20 over 28x plus 35. And then we have just actually two more steps to do. The next thing, we want to solve for dy dx. So we are going to multiply both sides by y over 1. And it's the entire side that gets multiplied by y over 1. So for that, our left side, the y's cancel, and we get dy dx is equal to, and then on the right side, I do have that y over 1 as a factor in front, but we know what y is worth. Y is worth the 7th root of x squared times 2x minus 7 cubed over 4x plus 5 to the 5th. So we want to replace our y with what it's worth. So we have the 7th root of x squared times 2x minus 7 cubed over 4x plus 5 to the 5th. That's from the y. And then open your brackets, and you've got 2 over 7x plus 6 over 14x minus 49 minus 20 over 28x plus 35. And that is the derivative of our original function using logarithmic differentiation.